All right, welcome back, and congratulations on completing the midterm and now being about halfway through the course. And our first post-midterm topic will be one that we've danced around but not really hit head-on just yet, and it's one that you might have been wondering when we were going to get around to, and that is glaciers and ice in Antarctica. And Antarctica is pretty much covered in glaciers and ice, so of course we're going to devote some time to that. And now that you have some geography and some climatology under your belt, you should now hopefully have an idea of just why Antarctica is so icy. And this lecture and the next will delve into different aspects of glaciers. This first lecture will introduce the water cycle, define glaciers, and introduce several categories of glaciers based on physical form in the first half, and we'll switch to introducing the concept of ice streams, as well as talking about how glaciers flow to the ocean and what happens when glaciers meet the ocean, as well as the differences between sea ice and the ice shelves that actually flow from the glaciers in the second half of this lecture. Wednesday's lecture, meanwhile, will focus more on how glaciers move and function as the rivers of Antarctica and how the different means by which glaciers flow, as well as how glaciers erode the rocks underneath and around them. So in regards to the midterm, I would still really prefer if people don't talk about it. I will add the extra credit points for those who have already turned in extra credit submissions later this week. And there is a lab due this Friday on the fossils of Antarctica. Aside from reading the TA presentation and getting help from them before Friday, February 12th at 11:59 p.m., which is when it is due, it may be worth reviewing lectures 6 and 7a, because those cover fossils and concepts like the difference between body and trace fossils and how you can use depositional environment to infer, or how you can use fossils to determine the depositional environment, such as seeing corals and figuring out that it was warm, shallow water. And another thing I want to mention is that the first reading assignment is due this Sunday, February 14th at 11:59 p.m. So if you have not already found a news article, this is the time to do it. Now, feel free to ask me for input if you want me to look at an article you're interested in, and I'm very happy to give you a sense of if I find it interesting, if it seems like a reliable source. Speaking of extra credit, by the way, I am making a new option available. In addition to doing a write-up on a colloquium talk or a write-up on a hike or excursion related to nature or geology, I am now making it so that you can also watch a documentary movie or TV episode about Antarctica and do a write-up about that. So 300 to 400 words, which is the same length as the other extra credit options. And you are very welcome to use the movies that I've assigned. But if you do pick another, it's completely fine. Just I'm looking for something that has a lot of educational content. So that's why I generally prefer documentaries and the like. Now, in case you need a reminder, these are the various stipulations for assignment number 1 again, and it's a very open-ended assignment about whatever article you choose. I am quite open to what you choose. There have been recent findings of earthquakes off the coast of Antarctica that are related to subduction in the trench off the subantarctic islands. There was also an amusing little article about a lost wallet from Antarctica turning up elsewhere years later that a student showed me. And I'm interested in anything like that. You really just need to make sure that your news source is reliable and that you link the article so I can figure that out, and that you meet the word count, like you've written enough about the article, and that you answer the prompts. I want a summary of the article because there's a good chance that me or the TAs have not seen it, and a response to the questions, what in this article had you not previously known about Antarctica? And following up on that, what about that was interesting to you? And remember, this is not a scientific journal article. This is meant to be like a news article. So basically a news agency writing about something cool found in Antarctica, but not directly what the scientists themselves are publishing. That's what the second assignment relates to. So we will begin with a short overview of the water cycle today to put things in perspective, and then we'll talk about glaciers in Antarctica and discuss some physical variations of glaciers. The second half of the lecture will focus more on some basics of glacial movement, like the existence of ice streams, as well as what happens to glaciers when they meet the ocean. And then a little bit about sea ice and how sea ice is very different and a completely separate feature from the ice shelves that are the actual extensions of glaciers. So there's a good chance that you've seen a diagram like the one on this slide before. A cycle that shows how some substance of interest, like water or carbon or nitrogen, flows between different locations. And those different locations are known as reservoirs. Reservoir is a term that you might have come across specifically when learning about an artificial lake. Lake Cachuma, near Santa Barbara, which is the main source of water for the area, is a reservoir in that sense. It's an artificial lake, but it's also a reservoir in the more general sense that it's a place where water is stored. And in that general sense, a reservoir is any place where water, in this particular case, or whatever substance you're interested in, resides. So in the case of water, reservoirs can be places like oceans, freshwater lakes, rivers, clouds, plants, soil moisture, groundwater, and glaciers. And that's where glaciers in Antarctica come into this. Now, some of the text on this diagram refers to those specific reservoirs like wetlands and oceans. Others go along with the arrows to indicate movement of water between those reservoirs, like evaporation when liquid water becomes gaseous water and joins the atmosphere, or precipitation when water condenses into either rain or snow and falls. And precipitation is one particularly important form of water transfer. It refers to rainfall or snowfall, and in Antarctica, we're mostly going to be concerned with snowfall because it's the snowfall that builds the glaciers that cover the continent. And a term I want to introduce, two terms actually, are accumulation and ablation in the context of glaciers. Because when glaciers are getting bigger, like in the zone in the center of the continent where snow is accumulating, well, that's the zone of accumulation. That's where the glaciers are getting bigger. Now, because glaciers flow towards the edges of the continent, they get farther and farther from where the snow is accumulating. And glaciers close to their termini, close to the end of the glaciers, are said to be ablating. Glaciers are getting smaller when they are being evaporated or sublimated, when the ice turns directly into water vapor, or when the ice melts, or simply when the ice breaks off into smaller pieces, icebergs, and does a process known as calving that we'll go over much more in the second half of the lecture. And both accumulation and ablation involve a transfer of water between reservoirs. During the case of accumulation, water is being transferred from the clouds to glaciers by precipitation, and during ablation, water is being transferred either back to the atmosphere by sublimation or back to the oceans by melting. And something really interesting to me about glaciers is that ice in general takes up most of the available freshwater on Earth. Glaciers, as well as sea ice, which is actually going to be freshwater because the sea ice doesn't actually incorporate the salt in seawater when it freezes. Glaciers and all of that ice are actually where most of Earth's freshwater is. And with all of the water on Earth, only about 2.5% of all the water on Earth is freshwater. The rest is mostly in the oceans, and the oceans are going to be undrinkable due to the salt. Now, of the very small 2.5% of the world's water that is freshwater, about 2/3 of that is locked up in solid form, in glaciers and sea ice and other forms of ice. And as we'll learn, a huge percentage of that is actually locked up in the East Antarctic ice sheets in particular. The East Antarctic ice sheet is the largest glacier in the entire world. And something interesting is that groundwater actually makes up most of the remaining third that isn't frozen. And groundwater is sometimes relatively easy to access if it's close to the surface, but a lot of the time it's too deep for humans to easily get. So most of the water that is available to humans is surface water, water in lakes and rivers, and that is a tiny percentage of the already tiny percentage of freshwater on Earth. And the thing is that Earth is overall in a pretty dry period of its history. So much of Earth's water right now is locked up in the ice caps, and more would be free to circulate if there were no ice caps, as was true during the dinosaur age. Now, that would mean that some of it would just add to the oceans to rise, but overall, global humidity was a lot stronger during much of the dinosaur age because there was more water available to circulate and less trapped up in the ice sheets. And even right now, when we're in what's called an interglacial period within an ice age, there are still glaciers, there are still ice sheets, there are still large glaciers covering continents at all, and that still locks up a considerable amount of water on Earth. And here's a visual depiction of that to give some perspective. There's 3 dots on here, and there's the largest, so what they've done here is imagine what Earth would look like if you took all the water out. You can actually see the ocean is kind of a flat plain now, and you can see the mid-ocean ridge. This largest bulb of water, this largest sphere of water in the center of the North American continent is all of the water available on Earth, as in an estimate of how much water there is underground on the Earth, frozen up in the ice caps and in the atmosphere. Now, there's a smaller dot to the right of that in what's now Kentucky, in what's Kentucky, more or less. And that is all of the liquid fresh water on Earth. So that excludes the ice caps. So you see that there's very little liquid fresh water on Earth. You can see just how much of that is caught up in groundwater. If you try to find the smallest dot, if you look closely, it is just north of Florida. It's very, very hard to see. But that is how much actual water there is in freshwater lakes and rivers. So again, not very much. And it drives home just how little fresh water is actually available at the surface for people to use. A lot of the water is locked up in glaciers. And let's talk about what a glacier actually is. A glacier is an accumulation of compacted snow. The ice in the glacier compacts under its own weight, and the glacier also actually moves under its own weight. And yes, glaciers move. Glaciers move downhill extremely slowly, and we'll delve more into some specifics of their movement next lecture. They form when there is more snowfall than snow melt, and this is the case in Antarctica, in some cases even at the coast. It's so cold in Antarctica, especially in the interior, that what snow does fall has time to sit there without melting, even though there's not much precipitation to begin with, because Antarctica is a high pressure zone. But what little snowfall does occur has time to pile up without melting, and it compacts. Snow becomes ice as it becomes compact, and and the ice becomes less porous, meaning there's less airspace in it and that it's more compacted, and also very impermeable, meaning that the pore space, the airspace in the glacier is not connected, that you have compacted ice and then small isolated air pockets. And this is what we'll come back to when we talk about how ice cores are used to measure climate change, because it turns out glacial ice is compacted enough, it's so not porous and so impermeable that the air gets trapped. So an ice sheet is the particular type of glacier found in Antarctica, and an ice sheet is a glacier that is more than 50,000 square kilometers. And there's only 3 true examples of ice sheets remaining today. There's the Greenland ice sheet, which covers all of the Greenland subcontinent, as well as the East and West Antarctic ice sheets. And during the last glacial episode of the current ice age, ice sheets covered a lot more than this. Ice sheets covered most of North America, as well as large portions of Europe. And glaciers need lots of snowfall to occur. In Antarctica, something I want to draw your attention to is that the center of the continent is going to be here, the zone of accumulation. That's where, to a big extent, the glaciers are flowing from. In the case of East Antarctica, the ice is accumulating at the center of the ice sheet and flowing outwards in all directions. For the West Antarctic ice sheet, the ice is flowing from kind of the boundary between East and West Antarctica and flowing westward and northward towards the ocean, towards the zone of ablation, where you have the glacier sublimating and melting and overall being destroyed. Now, I actually have a visual representation here of what the Earth is projected to have looked like during the last glacial maximum. And essentially the entire country of Canada and a lot of the northern US was covered in ice, as was most of Europe north of the Balkans and the Alps. And these ice sheets are now gone. This is from the Pleistocene, the next to the epoch before the current one. So we are living in the Holocene Epoch of the Cenozoic era. Prior to that was the Pleistocene Epoch, which was largely defined by the glacial maximum occurring at that time. It was a glacial period, meaning that glaciers were at their maximum. We are presently living in what's known as an interglacial period, where we still have ice sheets, but they've shrunk back to covering just Greenland and just Antarctica, as opposed to covering all of this extra land. So now we'll talk about the remaining ice sheets we have, starting with the 2 Antarctic ice sheets, because this is Antarctica after all. And you've certainly heard by now, definitely from me, that Antarctica is mostly covered in ice, and that most of the ice covering Antarctica belongs to the 2 ice sheets, the East and West Antarctic ice sheets. And combined, they are more than 1.5 times the size of the continental United States. Speaking of the continental United States, the entire Mississippi River system, so not just the Mississippi River itself, but the vast majority of tributaries like the Arkansas and the Missouri River, that entire system would take 50,000 years to completely drain all of the meltwater that we would get if you melted the entire combined West and Eastern Arctic ice sheets. It is a lot of ice. And the Eastern Arctic ice sheet is by far the larger one. It is over 4 kilometers thick at its thickest point, and it covers the entirety of the East Antarctic Craton. And you may remember me mentioning the fact that it flows divergently. We'll talk more about that, but that means that the ice is accumulating near the center and flowing outward in all directions. Well, it's all north, but flowing sort of up, down, right, and left, and emptying out at the various seas. And the Western Arctic ice sheet is a lot smaller. It's slightly larger than the ice. It's slightly smaller than the ice sheet that covers Greenland by itself, and it actually flows convergently. The ice accumulates near the boundary of East Antarctica and flows out northward and westward, mostly towards the peninsula. And West Antarctica is presently melting, and the Western Arctic ice sheet is losing ice rapidly. A lot of this relates to the fact that it terminates in the peninsula, which is experiencing the most notable warming on the continent. The peninsula is surrounded by the ocean, which is rapidly warming, and that's causing the glacier, that's causing the part of the glacier that touches the ocean to melt and get smaller, and that's having consequences up glacier, shall we say. And for a comparison, the ice sheet in Greenland, is a bit bigger than the Western Arctic ice sheet, but compared to the combined Antarctic ice sheets, it's tiny, just because the Eastern Arctic ice sheet is so darn big. Now, it covers a much smaller area of land. It covers Greenland, which is kind of a small continent in its own right. It's often considered the largest island, but it's like a small continent, basically. And it's the only ice sheet outside of Antarctica. The interesting thing is that if you look at a satellite picture of the Arctic and see white covering the North Pole, this is not a glacier. This is sea ice that formed from the ocean water freezing, whereas the glacier forms from snow accumulating on land and flowing out towards the oceans. And the Arctic is overall warming a lot faster than the Antarctic, and a lot of this has to do with the fact that the oceans are warming so much. Greenland is surrounded by the warming Arctic Ocean, and it's seeing higher and higher air temperatures, and thus higher melt anomalies, which refer to greater than expected degrees of melting in its ice sheet. Now, if you look closely here, you might see a little splotch of ice in Iceland, which is kind of ironically named because there's much less ice covering the island of Iceland than there is the continent of Greenland. Anyhow, the tiny dots, the tiny white dots blown up here, are what's known as ice caps. And ice caps and ice sheets are two separate types of a broader category of glacier known as continental glacier. Glaciers are to a big extent defined by the surrounding topography, by the valleys they flow through, or the mountains that confine them. But if a glacier isn't really confined by mountains or valleys, if it just covers everything, like you can see how it's just kind of this white blob in the middle of the island, it's known as a continental glacier. If a continental glacier is larger than 50,000 kilometers squared, it's an ice sheet. And you have those couple examples like Greenland and the two Antarctic ice sheets that cover the whole continent. If it's smaller than 50,000 kilometers squared, it's known as an ice cap. And the ice caps found in Iceland, as well as on Baffin Island, are remnants of ice sheets that actually covered much more of these islands during the most recent ice age. And the ice caps don't actually cover everything. They don't cover the whole continent, but they still kind of exist. They're not confined by the valley surrounding them. Now, most glaciers, if we're going to talk about physical forms of glaciers, are going to be somewhat defined by the topography surrounding them. Something that I find is crucial to understanding glaciers is realizing that glaciers don't stay the same throughout their life. It's hard to say when a glacier's life begins and ends, but they form where snow is accumulating and they end wherever the snow is ablating. And over the course of that life, they'll take several different forms, often depending on how the rate of accumulation kind of balances with the surrounding topography. So the glaciers found outside of Antarctica and Greenland and Iceland are not continental glaciers, They begin, they are usually known as alpine glaciers instead, and alpine glaciers are those glaciers that are confined by the morphology of the surrounding mountains. Um, and Alpine glaciers are going to be relatively narrow when compared to ice sheets, but they're quite wide when compared to a river of liquid water. And as we'll talk more about in the next lecture, glaciers erode the rock underneath them, they break it down. And because glaciers are wide and solid and they don't compact easily, and because they flow so slowly, they kind of slowly carve out everything surrounding them rather than rapidly cutting down like a river does. And so they make what's called a U-shaped valley. Alpine glaciers often get their start in these particular U-shaped bowls called cirques, named after the French word for circus, like Cirque du Soleil. A cirque is going to be surrounded on three sides by mountain. You'll notice that the mountain is kind of curved. That's from ice carving out the mountain, because ice makes kind of a bowl-shaped, well, it makes a bowl-shaped valley when it erodes, as opposed to a river. When a cirque glacier accumulates enough that it starts to flow downward, it becomes an alpine glacier. And the takeaway is that glaciers evolve. And not all glaciers start like this. Some glaciers start as ice sheets, some glaciers start as cirque glaciers, but they become different types of glaciers as they move. Case in point, as an alpine glacier widens out into a wider valley, it'll often become known as a valley glacier instead. And valley glaciers flow much more slowly. Now, the interesting thing is that the Antarctic ice sheets become valley glaciers as they become closer to the coasts, far from the zone of accumulation and closer to the confining transantarctic mountains. Glaciers flowing from the interior of the continent will become trapped by the transantarctic mountains or by other mountains that are exposed near the coast, and thus individual lobes of those glaciers will be constrained by the valleys between those mountains. Now, something really interesting that happens after that is when you have glaciers flowing through a narrow valley that suddenly take on a different shape if that narrow valley gives way to a wider valley or to a plain. And this is a really good example of how glaciers take the shape of what is confining them to a large extent, unless you have enough ice mass that it just covers everything else. But further away from the zone of accumulation, further away from where the glaciers are accumulating, glaciers are going to be much more dependent on the surrounding morphology, the surrounding mountains, the valleys they're going through. And in this upper example, you can see how an ice sheet glacier, the East Antarctic ice sheet, gets trapped into this valley in the transantarctic mountains, and it narrows, and then as soon as it exits the valley, it spreads outward in all directions on this plain. Now, this is a Piedmont glacier. Piedmont refers to foot of mountain, and the town of Piedmont, California is named after the Oakland foothills. The Piedmont region of North Carolina refers to the fact that it's in the foothills of the Appalachians. And likewise, a Piedmont glacier is coming down from the mountains and spreading out in all directions as it enters a wider valley or a plain. And notice how the glacier, it's kind of like what you would expect water to do, but in slow motion. Water would flow through here and then spread out in all directions. It kind of makes a fan shape. And this is kind of where it ends. As the glacier spreads out, this actually exposes more of the surface area of the ice to ablation or to melting. And so this often is where the glacier ends. The glacier ends up melting and ablating more as it gets spread out and as more surface area is exposed. But this isn't what happens to all glaciers. Some glaciers actually do reach the sea, and we'll talk more about what happens in those cases in the next half of the lecture.